Good evening. Welcome to the 2020 BioTech 201, Molecules of Life. It is so fantastic to see you tonight. As you might have guessed, we're doing some things a little bit differently this season. We'll get into that a little bit more as we move through the next hour and a half together. We've got a full house. We are packed fuller than we have ever been for BioTech 201. So that means we're going to need to do things a little bit differently. We need to recognize that we're a little bit cozier. As we work through some of our activities tonight, just give yourself and your neighbor a little bit of space and a little bit of grace and help them out if they need it. I promise the bag that you were given when you came in is not your snack. I promise. You will be eating what is in that bag if you so choose, but there are cookies that are coming after. I promise. I promise. Yes. Okay, so let me start by saying that we have some fantastic folks that I want to say thank you to right off the bat. So our presenting sponsor for this year's BioTech 201 is the James Cecil and Margaret Ashburn Foundation. Many of you may know the Ashburn Foundation, many of you may not, but they are a huge supporter of the community of different events throughout the city. And they are our presenting sponsor, and they are one of the reasons why we're able to offer 201 and all the things associated with it this year at no cost to you. I also want to say a special shout out to our three presenting sponsors. So the Jackson Center, don't you love being in the Jackson Center? Yes. It's just fantastic space. And I know that you love the Jackson Center cookies, because I've already heard that from you, yes. I also want to say a special thanks to Orange Beard. So JP has done our videoing for BioTech 201 for I think about 5 years, and all those of you that are watching us online, it's thanks to Orange Beard, and we really appreciate that. And then I also want to say a special thank you to the Fantasy Playhouse. So as you might have guessed, I am not in my typical HudsonAlpha blue or my blue vest. And I will not be in HudsonAlpha blue or the blue vest at any point over the next month. Because each of the stories that we're going to talk about has a historical connection to it. Each week, I will be in some different historical outfit. Most of those courtesy of Fantasy Playhouse. And I also want to say a special shout out to Mary Lamb, my mom, because she provided all the tailoring so that I could actually fit and wear all of these fantastic outfits. I promise you there are some spectacular articles of clothing coming over the next several weeks. So with that, let's get started. We have so much to cover. Don't we always have so much to cover? We are going to talk about the biomolecules of life. That's a much better title than Let's Do Biochemistry, right? You might not have come if I said Let's Do Biochemistry. But we're going to talk about the chemicals that actually make you and me us, that are present in every living organism and what they do. And there are 4 broad categories. Lipids, which are oils and fats. We'll talk about that tonight. Proteins and all the variety of proteins. Carbohydrates and nucleic acids, DNA and RNA. And the key concept around each of these are made up of a relatively small number of atoms of key elements, which you can see on the screen behind me. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And we abbreviate each of those with their capital letter. This small number of elements, atoms of these elements, are what make up you and me. So in order for us to talk about how these molecules are put together, we need to talk a little bit about chemistry. Okay. If you are not a fan of all things chemistry, if you do not get up in the morning thinking about chemistry and chemical bonds, you do not draw out chemical bonds in your sleep, I promise our goal is to keep this at a relatively general level. If you are a huge fan of chemistry, you're going to find that I'm still keeping this at a general level. We're going to dip in just enough to keep everybody engaged. The point I want to make is I don't want you to be able to memorize and recite back specific chemical structures. I want you to look for key patterns and for what's different and what's similar and how are these things unique and what do these uniquenesses tell us about ourselves and about our world. So a compound is any molecule made of atoms of more than one element. So carbon dioxide, carbon and 2 molecules of oxygen, that's a compound. Glucose, made up of carbons, hydrogens, and oxygens, that's a compound. And these different atoms, these carbons, hydrogens, and oxygens, are bound together. They're held together with bonds. We're going to talk about one specific type of bond. We're just going to mention it, and that's called covalent. Covalent bonds are the key that we're going to focus on, and covalent bonds are when 2 different atoms share their electrons. So they share a part of themselves. Atoms are happiest when they have kind of a full component of electrons around them. Kind of like, mom is happiest when all her kids are home. Atoms are happiest when they've got all the electrons. And if they don't have all the electrons on their own, they're going to share electrons with their neighbor. And they'll say, I'll hand you the electron to hang on for a while, and you hand it back to me, and you hand me your electron, and we'll hang out together for a while. So there's this sharing that goes on, and that sharing holds those different elements together. That's about as deep as we're going to get in the whole concept of covalent bonding, but there's a sharing. And the shortcut that you can remember for this is that hydrogen atoms have 1 bond. They share 1 pair of electrons. Because they only have 1, that's exactly right. Oxygen makes 2 bonds. They share 2 pairs of electrons. Nitrogen shares 3 bonds, and carbon shares 4 bonds. So carbon likes to bond with 4 other things. So these different things, when you see something like this, CH4, you can see that our carbon, the C in the center, the lines indicate bonds, the letters indicate atoms. Carbon in the center, the C, has 4 bonds to 4 different hydrogens. Each hydrogen has 1 bond to carbon. So this molecule, CH4, is methane. This is also swamp gas. And it's written this way. But this image doesn't really tell you how the molecules, how the atoms of hydrogen and carbon are arranged. So for that, you want to look at something like this behind me, which is called the ball and stick model, which gives you a sense of how each of these molecules are arranged. The carbon is the black circle in the center, and then the ball and the 4 white balls and the sticks, that's where the hydrogens are. And you can see it sort of forms a pyramid type shape. You may also see it what's called a space-filling molecule. Same general arrangement, but it's just occupying more space than the ball and stick. So most of what we're going to talk about is going to be in this general, I'm going to give you one of these kinds of illustrations or these kinds of depictions of our molecules. Here's a different one. This is acetic acid. This is found in vinegar. This is the primary component of vinegar. You're going to see this molecule, this C, double bonded to an oxygen, and then an oxygen and a hydrogen. You're going to see this a lot. This is an acid group. And again, if we count, this carbon makes 4 bonds. 1 to this hydrogen, 1 to this hydrogen, 1 to this hydrogen, and 1 to this carbon. This carbon makes a bond to the other carbon, a bond to the oxygen, and 2 bonds. It's called a double bond to the oxygen. So that's where our 4 total come from. This oxygen makes 2 bonds to the carbon. This oxygen makes 2 bonds, 1 to the carbon and 1 to the hydrogen, and this hydrogen makes 1 bond. So it fits that concept of what we just talked about. Here's the structure. Here's the ball and stick and the space-filling structure. Just to give you a sense of kind of 3-dimensionally what these pieces look like. And again, just to be clear, I do not want you to go home tonight. I don't want you to walk home anyway, but I don't want you to go home and draw out these structures. That is not the goal of the class. I want you to see broad themes, and I want us to understand how the structure of molecules defines their shape, which gives them the function that they need to carry out their job. Okay, here's a more complex chemical structure. And you've got all of these in your handouts. Feel free to flip back and refer to them as we go. All right, so let's count the number of carbons in this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 carbons. There's a double bond. There's a double bond. And there's my acid group, my double bond O and my OH. That is a lot to write. There's a lot of complexity there. So let's simplify that a little bit. Let's just write out the chain of carbons. The hydrogens are still there, we're just not going to include them. That immediately gives you a sense of what the actual molecule looks like in terms of structure. We can simplify that down even more, though, and take out the letters and just join them together. And so every place at the end of each one of these lines, we know there's a carbon. There's a carbon here, there's a carbon here, a carbon here, all the way around. And you can see this is a much easier molecule to visually get a grasp of than all this up here. So sometimes I'm just going to show you something that looks like this. And again, I don't expect you to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, count the carbons. I just want you to get a sense of there's a lot of carbons and there's a lot of hydrogens that I'm not showing you, but it's a chain of hydrogens and carbons. And then the three-dimensional structure, the ball and stick and the space-filling model, you can see that there's a curve to these molecules. The double bonds, these double bonds, kink the chain and cause it to actually have a curvature to it. And as you might imagine, a molecule with a curvature is going to have a slightly different function than a molecule that is flat in a linear plane. All of the things that I've just shown you on the last two slides, these all represent linoleic acid. This is a fat that we're going to talk a lot about in just a little while. But I've just shown you multiple representations. Okay, so at this moment, if you are wondering if you made a bad decision to come to Biotech 201, if you online are considering if maybe it would be better to actually flip to whatever is on television, let me just reassure you, we aren't going any deeper in terms of chemistry than that. I want us to get, again, broad themes, broad pictures. And I promise there's going to be interactive times, remember the thing that's in your bag, and we're going to tie some history in. So let's actually start by grounding tonight's discussion about lipids in a historical context. So I'm going to start with an ancient legend. So as the legend tells it, long time ago, the king of a particular city-state in Greece was looking for a deity, a god or a goddess, to be the patron of this city, to protect this city in times of war, to provide prosperity, to have the blessings of the god or goddess on the city. So this particular king essentially put out an all-call, put out an RFP, and said a request for proposals, or actually an RFD, a request for deity, and said, I'm looking for a god or goddess who would like to be the patron of my phenomenal city-state. Well, as it turns out, two deities, a god and a goddess, both thought that they would be the ideal patron of this city-state. Athena and Poseidon. And there was actually a lot of discussion and debate, and they almost came to blows as to which one was going to be the patron of this city. And then the king stepped in and said, let's have a contest. This king was quite a wise politician because he said, I'd like each of you to present a gift for the citizens of my city. And then I'll judge which gift is the best, and the winner actually will become the deity. That's pretty shrewd because you actually get two gifts from two different deities, both of which hopefully are going to benefit your people. So Poseidon goes first. So all the people gather up on a mountain just at the center of the city. They all watch. And Poseidon goes first. And you know, Poseidon has a trident, a three-pronged spear. And Poseidon hurls his trident into the ground. And at that spot, a bubbling spring comes up and a lake soon forms. And you can hear the people, ooh, water, ah. But as they get closer, they discover that the lake is salty. Because remember, Poseidon is the god of the seas and the ocean. And so the only water that he controls is salt water. So that kind of puts a damper on that gift. But still, there is water around. So then Athena steps up to the plate. And in much less dramatic fashion, she turns and she puts something in the ground and she steps back, and a gorgeous, huge olive tree springs up. And the people realize immediately this olive tree provides food. This olive tree provides oil for our lamps to light the darkness. This olive tree provides wood for our boats and for our houses. And so the king declares that Athena's gift is the better gift, and that Athena will be the patron of the city, which will bear her name, Athens. And that's the history, the legend of the naming of the city of Athens. Now, Poseidon is not very happy about this, and the legend continues to say that he then floods the entire country. Sore loser, but this contest between Athena and Poseidon is captured in all different kinds of art, like what's on the screen behind me. And if you go to the Acropolis in Athens, on the rear pediment of the temple of Athena are the remains of, this is a reconstruction on the screen behind me, the remains of this entire contest between Athena and Poseidon. And next to the temple of Athena, you will find an olive tree. And an olive tree has been there as long as anyone can remember, as a reminder of the role of Athena and the olive tree in the history and the naming of the city. There's the olive tree, sorry. So, in the Mediterranean, the olive tree is an incredible part of the culture and the economy of the countries that surround the Mediterranean basin. I don't know how much you know about olives. They require a short, cold winter and a long, hot summer. And the Mediterranean provides that in spades. The olive tree not only provides food, but as I said earlier, provides oil and provides wood. Olive trees grow in rocky soil. They send out a really long taproot, and their leaves are designed in such a way that it minimizes water loss through evaporation. So olive trees do really well in dry climates. Olive trees are also incredibly hardy. You can have an olive tree that is chopped down or that is burned, and the next spring, shoots will come up from the stump and ultimately fruit out into full olives and olive production. The olive tree trunk is incredibly strong. Legend has it that Hercules, the staff of Hercules, was an olive tree. The oil of the olive, Homer called liquid gold. In addition to being used to cook with, it was used to light lamps. It was rubbed into the hair and the skin as a cosmetic beauty ritual. Herbs were put into the oil, and the essence of the herbs seeped into the oil, and physicians prescribed herbal olive oils for a whole host of things, from indigestion to ulcers to insomnia. So the olive was incredibly important in that culture. If you think about it, if you go back to Scripture, to the Bible, there are over 150 references to olives and olive trees and olive oil. Those of you that know your Scriptures will remember that the dove brought back an olive branch to Noah after the flood. You might remember that the Good Samaritan binds up the wounds of the individual who's been attacked by robbers with olive oil and vinegar. The Mount of Olives, the parable of the virgins with their 10 lamps with olive oil. So throughout this entire area, you can look at Egyptian history, you can look at African cultures and civilization, Greek, Italian. The olive figures really prominently in those stories. The olive tree became a symbol of peace and prosperity, in large part because olives were plentiful and olive oil was plentiful in times of peace and absent in times of war. And we still use that language when we say, I'm extending an olive branch of peace. It comes back to that original concept. And in the ancient Olympic Games, the winners of each event were given a wreath made of olives, of olive leaves, and then they were given a special supply of olive oil, high quality, and I don't just mean like a jug, I mean like thousands, well, maybe hundreds of jugs of olive oil that they could then in turn sell at a high price. So there was some income that the winners of the Olympic Games made. And the oil was generally stored in amphora that looked something like this. They were sealed, and they had an inscription on them from the event of the victor from the early Olympic Games. So olives are harvested from the tree, and then they are ground into a paste, either mechanically or by stone. This is a stone olive grinder in Croatia. And so you get this thick olivey paste, the pits, the seeds, and the fruit. And then it's spread on these mats. And you can see these big round mats. The olive paste is spread on the mats. And then the mats are stacked in a vertical press. And every 5 or 6 mats, you put a steel plate. And then you apply pressure and you express the oil out of the paste. And that oil is then collected and bottled and stored. Extra virgin olive oil is olive oil that's been collected through this process with no heat applied. So it is cold pressed. It retains all of the flavor of the original olives. But only a small amount of olive oil meets the quality standards of extra virgin. The rest of the olive oils then have to have their impurities removed, and that often involves heat. And heat destroys many of the flavor compounds. A little bit of the extra virgin olive oil is mixed back in, but that's why regular non-extra virgin olive oil has a slightly different color and a very different flavor profile. Works great for cooking if you're going to saute something, but you want to hold the extra virgin olive oil for drizzling on salads and for dipping your bread and all those kinds of things in. So the olive was critical to early Grecian and Egyptian and Roman civilizations as an oil, as a fruit, and as wood. Olive oil is a lipid. That's one of our 4 biomolecules we're going to talk about today. There are some key categories of lipids: oils and fats, waxes, phospholipids, which form the membranes around cells, and steroids. We're going to spend most of our time talking about oils and fats and a little bit of time on phospholipids. We won't have time to dig into waxes or steroids, but they fall under the category of lipid. And there are some key commonalities across the lipids. Generally, they do not mix well with water. They stay separate. They mix poorly, if at all. And they are primarily made of long chains of carbons and hydrogens. So that image that I showed you a few slides ago with 18 carbons and all those hydrogens, that is one of the fats, linoleic acid. Actually, it's one of the fats that you find in olive oil. It's not the primary fat in olive oil. So in order to talk about lipids, there are 2 key things that we need to spend a little bit of time talking about. We're going to do the first one before the break. Then we're going to do some taste testing, take the break, and then do the second one. So the first one is fatty acids. So fatty acids are a key part of lipids. They are long chains of carbons and hydrogens. Let me show you an example. So this one, 4 carbons, 1, 2, 3, 4. Here's our hydrogens all the way around, and here's that acid group, the C double bonded to the O and then the OH. This is butyric acid. Here's what it looks like in the ball and stick model. Here's the shortcut version on the far left. And here's a 3-dimensional version that we created. It looks a little bit like an animal, doesn't it? Like, high on the hills to the lonely goat. Okay, but anyway, the way this works, so the dark spheres are your carbons. Do I have this the right way? Yes. except I need to flip it, well, we would flip it around because there's our double bond O, and here is our OH. But anyway, so you can see the light balls are the hydrogens, the dark balls are the carbons, and the reds are the oxygen. And you can see the carbons are in sort of a zigzag pattern, and you can see that the hydrogens roughly align either along the top or along the bottom. So this is butyric acid. You like butyric acid. Butyric acid is found in butter, and it is the flavor compound that makes butter taste like butter. So researchers have come up with artificial butyric acid that they can add to foods to give it a butter-like flavoring. But this is a really handy molecule, especially if you are Paula Deen. So let's see if I can get that on. Each week, we'll have an example molecule in 3D. You're welcome to come up, to touch it, to look at the way it's created, because I know sometimes looking at pictures on the screen is challenging. So we wanted to have 3D models. I have the most phenomenal team. We took balloons, we wrapped balloons in yarn coated in glue, and then solidified, sprayed like, I don't know, like shellac on it, I don't know what. But anyway, to get these fantastic molecules. Okay, now, so that's butyric acid, 4 carbons. Here's a whole set of other fatty acids, and you can see they're different sizes, 12 carbons, 14, 16, 18. Again, the specific concept isn't important, just the general theme that they come in different lengths. These fatty acids are saturated fatty acids. I'm willing to bet many of you have heard of saturated fatty acids. Yeah. These are the things that taste really good, but health-wise are not so good for you. Saturated fatty acids mean that if you look at every carbon, it has 4 bonds. It has 4 individual bonds. It has hydrogen, so it may be bound to 2 things, a carbon on either side, and then it's got 2 hydrogens. It is saturated with hydrogens. So that's what a saturated fatty acid means. There are as many hydrogens as it possibly can take in this molecule have been packed into this molecule. Now let's compare that to this, and here's what the structure looks like. And so you could see, here's a carbon, there's a bond to one, there's a bond to another, and there are our 2 hydrogens. There's our 2 hydrogens. So we have packed this molecule full of hydrogens. Now let's look at this one. These sets of fatty acids are clearly different. 2 things that are different about this. Again, we're just looking for broad patterns. We've got double bonds. That's what this is. So what this means is, instead of I'm attached to a carbon, I'm attached to a carbon, I'm attached to a hydrogen, I'm attached to a hydrogen, instead of that, what we've got is carbon, hydrogen, double bond. Ooh, that doesn't work so well. Double bond. Y'all are really glad that I have on shorts, aren't you? So that double bond does a couple different things. So it is not fully saturated anymore, because I could have attached to a hydrogen, but I've got a double bond. And it also introduces a kink. So you can see that instead of having this zigzag straight across, I've now introduced an angle. And the increasing numbers of double bonds increases the bend, increases the kink. Everybody see that? These are unsaturated fatty acids. If you've got a single double bond, they are monounsaturated fatty acids. If you've got more than one double bond, they are polyunsaturated fatty acids. These are the fatty acids that generally are better, healthier for us. There'll be some caveats in this, but generally, unsaturated fatty acids have a better health profile for you. They reduce or neutralize, let me say that differently. Saturated fatty acids increase your risk of cardiovascular disease. Monounsaturated fatty acids have a neutral risk, and polyunsaturated reduce your risk. So we hear a lot about fat and about saturated and unsaturated fats. They've got a kink in them, and that kink is going to be important in just a little bit when we talk about the difference between solid fat, and liquid oil. But first, enough chemistry, let's taste some fats. Okay, so you have a swag bag of fat. This is kind of like going to the Oscars and you get your swag bag. This is your swag bag of lipids. Now, here's what I'm going to ask you to do, because we got 300 people that are going to try to do this all in the same room. And those of you that are watching from home, this is the time for you to go look into your kitchen and pull out your butter or your olive oil or your corn oil or your margarine, whatever you've got in your refrigerator or in your pantry, and bring it back with us as well. Okay, here's some key instructions. Put your hand out underneath your chair. You don't need your hand out right now. Stick it underneath your chair just to get it out of the way. All right, don't open the, I've already, too late. Many of you have already opened the bag. If you haven't opened the bag, don't open the bag yet. Hear me all the way through. What you're going to do when I tell you to is you're going to open the bag and you're going to take everything out. Set the water on the floor beside you. This is what you will sip in between tasting of lipids. This will cleanse your palate. You're also going to find a little plate that's going to hold all this stuff that we're going to taste test. Okay? We're going to taste test 4 different kinds of lipids. A butter, 2 margarines with different combinations of oils making up the margarines, and olive oil. So you're also going to find a wet wipe. Some of you might want to wipe your fingers before you get started. You're all going to probably want to wipe your fingers after you get started. You got 1 wet wipe. Use it well. Okay? Okay, here's what I'm going to have you do. Open the bag, put the water on the floor beside you, pull out the plate, open the bag, pull out the plate, I'm going to wipe my fingers. I should also say, you do not have to do this. Number 1, if you're allergic to any of these things, please don't do this. But this is just purely optional. No one will give you the evil eye if you do not play along with us. But we thought there's so much conversation about butters and fats and oils and saturated and unsaturated. Let's actually just experience them one after the other. Okay, here's the next thing I'm going to recommend that you do. I'm going to recommend that you open your crackers. These are unsalted crackers. Open the crackers, stick the crackers on your plate, and then put the wrapper in your bag. This is going to be your trash bag. We're going to collect everything in your trash bag. Okay, those of you that are playing along at home, you can use crackers, you can use bits of bread, you can just use your fingers. Any of that is completely acceptable. The goal is to taste different kinds of lipids, fats, and oils. All right, I'm going to suggest that you break your crackers into pieces, so that you've got a bit of cracker for each of your fats. Okay. All right, so let's start with your Grassland grade AA butter. Only the best for our biotech audience. Here's what I want you to think about as you taste all of these lipids. I want you to think about, how does it feel in your mouth? Is it dense? Is it airy? Does it melt easily? Does it not melt easily? Does it have a salty taste? Does it have a vegetable taste? Does it have an oily taste? We're going to work our way through. So let's start with butter. I love butter. I love butter. I just heard someone go, butter. I just dropped my butter. All right, so that's creamy. It has a lot of flavor to it, a lot of like depth of flavor. It is salted butter, and that's because most of the margarines are salted. So just to make it equal, we went with salted butter as well. It melts pretty quickly, but it lingers on my tongue. It kind of coats a little bit. It has a finish. Yeah, if we were talking about wine, we would talk about the nose of the butter and the finish of the butter, how it feels on the palate, all those things. All right, so that's the real thing. Okay, no judgment here, I promise. Butter comes from dairy. You're talking about cow, but you can also make butter from sheep or from goat or from camel, but it is a dairy product. And if you look at the saturated and unsaturated fats on the screen, and this is also on your handout, so don't worry about trying to write this down. You'll have this. 61% of the fat in butter is saturated fat. That is why it tastes so good. Monounsaturated, 31%, tiny little bit of polyunsaturated. And then there are some other categories of fats that we're not going to worry too much about. Okay, now let's move on to country crock. Country crock, this is a vegetable oil spread. This is 52% vegetable oil. The rest of it is primarily water. So it's emulsified in the water. Okay, tell me what you're tasting. What are you experiencing? Salt. Yeah, you know, it's kind of unfair that we start with butter, isn't it? I mean, you know, country crock tastes pretty good on its own on a hot muffin until you've just had some butter. And then it just kind of, but it is airier. It has more air and it's whipped, so it's not as dense. That's also a great marketing tool, so it's less calories because you're eating more air than actual product. You can buy whipped butter, which is all of the fat of butter, but it's got a whole lot of air in it, so it's better for you. What else do you taste in the country crock? It's oily. Yeah, it's slippery, slick, okay? So let's compare the fat profile. So much less saturated fat, 17% monounsaturated, and a whole lot of polyunsaturated, the good fat. It's primarily made from soybean oil, palm kernel, and palm oils. So the palm fruit tree has these fruits on it that are red, and if you open them up, you've got the fleshy fruit, and then you've got a big seed, a pit in it. If you extract oil from the fruit, that's palm oil. If you extract oil from the seed, it's palm kernel oil. Both palm oil and palm kernel oil have high amounts of saturated fat. They're solids at room temperature. Soybean oil has very little saturated fat. It's primarily mono and polyunsaturated fats, but it's a liquid. And so you've blended the solid palm and palm kernel with the liquid soybean to get country crock. Okay, now let's look at our next one. Let's look at Smart Balance. Smart Balance supports healthy cholesterol levels already within normal range. And so if you're already got good cholesterol, this is good for you. But if you got bad cholesterol, well, let's just leave that there. Okay, so let's give this a whirl. Somebody just said, "Ooh, this is terrible," and somebody else said, "This tastes great." So, you know, our own flavor profiles, our own preferences vary. Tell me what you taste different, or what you taste uniquely about this one. Salt, lots of salt, a lot of salt. Yep, it's oily, it's whipped again. It has a different flavor profile than country crock, and that's because it's made with different oils. Smart Balance is made with canola and olive oils as well as your solid palm oil. So we got a lot of olive oil. So if you are tasting some of the strength of olive oil, it's coming from the fact that there's olive oil in that. And then if you look at this flavor profile, It's got a lot of monounsaturated, not much different in terms of saturated, but unlike Country Crock, which has more polyunsaturated, Smart Balance has more monounsaturated. And monounsaturated helps, it's got a neutral risk. It won't raise your risk of cardiovascular disease, it won't drop your risk of cardiovascular disease. Okay, before we open the potentially messiest one, my recommendation is that you take all of the other fats, unless you just want to just lick that great big pat of butter one more time, and you take all the fats and all the lids and go ahead and put them in your trash bag, okay? All right. So now we've got our last package. We had to search to find individually packaged olive oils. And it actually is extra virgin olive oil, so let's just acknowledge that. You're getting cold pressed straight from the olive paste. There's a couple different ways that you can do this. I would not recommend you tear this right off. I would tear just to the opening, and you can either put it on your cracker. I'm going to put it straight on my finger, if I can get it open, with my slippery, lipid-soaked fingers. There we go. Okay. Just a dab will do you. Okay. Very olivey, understandably. It is olive oil, but it's got that very characteristic kind of salty, briny flavor profile. It lingers. It lingers on your tongue, and for me, kind of in the back of my throat. Very different than the other spreads that we've just tasted. That's obviously all from olive oil. And you can see that the fat profile, very little, relatively speaking, unsaturated fats, a whole lot of very little saturated fats, a whole lot of unsaturated fats. The primary fat in olive oil is, not surprisingly, oleic fatty acid, and it is the primary driver of the flavor profile, the fat that is in olive oil. So, 4 very different lipids. One that is naturally a solid at room temperature, one that is naturally a liquid at room temperature, and then these 2 margarines that are a combination of oils and fats, and we'll talk about how you actually take a liquid oil and turn it into a semi-solid product. But, okay, just out of curiosity, I'd like to know your favorite. So, I'm going to start from this end. How many of you olive oil is your favorite? Excellent. Y'all are following the Mediterranean diet. Well done. Very good. All right. Smart Balance. This has fans because it does have a healthy fat profile. Country Crock. Yep. Some of you are Country Crock fans. Butter. Yeah. Yeah. And therein lies the challenge. It tastes so good. So good. Okay, so put everything back in your bag. And then in just a second, we're going to go for our break. And so your reward after trying all these lipids is that you get cookies. So put everything in the bag. And then just leave the bag. We're going to take a break. Leave the bag in your chair, and my team's going to come through while everybody is at break, and we're going to grab all the bags and clear the space. Okay? So it is 7:15. We are going to take a 15-minute break. All right? 15-minute break. We're going to start back right at 7:30. Leave your bags in your chair, and we'll clear them out. So I'm told that there are 2 key things that make up fats, oils and fats. And the first one was fatty acids. And we talked about saturated fatty acids and unsaturated fatty acids. Our fatty acids join in groups of 3 to form a triglyceride. So, triglycerides are the way that fats generally are present in organisms, in animals, in plants, in you and I. And so what I've got on the board behind me is I've got 3 fatty acids. They're all saturated fatty acids, no double bonds in the carbon chains. And then I've got this molecule over here on the left-hand side that's called glycerol. 3 carbons with OH. And so you take 1 molecule of glycerol and 3 fatty acids, and you can see this process, this condensation process, where we pull out water, H2O, and we link each fatty acid to the glycerol chain. So this is a triglyceride. And you can see in this instance, I've shown all 3 fatty acids exactly the same. But triglycerides don't have to have all 3 the same. They can have 3 totally different fatty acids. They can have combination of saturated and monounsaturated or polyunsaturated. They can have 2 of one and 1 of the other. But it's that combination. So generally, when we talk about fats, they're not hanging out as individual fatty acids. They're in a triglyceride format. Now, given that, some triglycerides have a higher concentration of saturated fatty acids. Some have a higher concentration of unsaturated fatty acids. I'm showing you a triglyceride that's got 3 saturated fatty acids, and those saturated fatty acids pack together well. So I'm going to make a real small one. So this is the same thing, I've just made it real small. And they pack together really well. And this would actually be solid at room temperature. So butter, animal fat, lard, coconut oil, solids at room temperature because they are primarily composed of saturated fatty acids. And those saturated fatty acids pack together and are stable as a solid at room temperature. So that makes sense. Butter is a solid at room temperature, and I showed you butter is a whole lot of saturated fatty acids. Let's flip it over. Let's look at triglycerides made with unsaturated fatty acids. So here I've got, of my 3 fatty acids, 1 is saturated, 1 is monounsaturated, it's got a single double bond. 1 is polyunsaturated, it's got 2 double bonds. And you can see, remember I told you that double bonds create a kink. They change the order of how the molecules align and the best alignment of those molecules, and it introduces a kink in the chain. Those kinks in the chain don't pack well together. It's kind of like, if there's a whole bunch of you all packed together in an elevator and suddenly somebody stretches out their arms, everybody's got to spread apart some. Imagine lots of people in the elevator stretching out their arms. You can't get as many people in the elevator. The molecules don't pack down and they aren't solid, so at room temperature, they are oils. So by and large, your oils, things that are liquid at room temperature, have a higher concentration of unsaturated fats. Your solids have a higher concentration of saturated fats. That makes sense? I know we're covering a lot of chemistry, a lot, but these are words that I think you hear a lot, and I want to put some meaning behind them for you. How margarine was made. This is a lovely story. So, in the Napoleonic Wars, Napoleon said, I will give a reward to anyone who can make a butter substitute. And so an individual created the first margarine in 1869 by blending beef tallow, beef fat, solid beef fat, with milk or water. Clearly, this was not a health issue. This is not healthier than butter. But it was an issue of there were butter shortages, and this was something that could be got to the troops as a fat for sustenance. Around the turn of the century, about 1900, scientists began to develop other technologies that allowed you to replace beef tallow with vegetable oil. But you had to do something, because vegetable oil is a liquid, you had to do something called hydrogenation. So the process of hydrogenation, we are not going to go into it, but in a nutshell, you are pushing hydrogens to break up some of those double bonds, to take us from this pattern back to this pattern. So I am adding in hydrogens. So in this example here, I'm adding hydrogens. I'm not fully hydrogenating, I'm only partially hydrogenating. I'm just getting rid of some of my double bonds and taking some of those double bonds to single bonds. And what ends up happening is I introduce less kinks in my triglycerides, and there's enough of an ability to pack together that it is semi-solid at room temperature. So margarine, from about 1900 until about 2016, 2017, was created by taking oils and hydrogenating them and then creating semi-solids. So you saw lots of what are called hydrogenated fats. And as we as a society ate a lot more foods with fats packaged in them, they were hydrogenated fats. Now, here's the challenge. Hydrogenation creates trans fats. And trans fats are the dark side of lipids. Trans fats are not good for you. Trans fats increase your risk of cardiovascular disease. And it took about 30 years for the scientific evidence to accumulate to a point where everybody agreed, yep, trans fats are bad news. Here's how trans fats happen. This is the same reaction I showed you on the previous slide. I'm just going to make this really simple. I am just lettering the different carbons. So I'm just going from carbon 1 to carbon 2 to carbon 3 to carbon 4. And if it's above the line, I've made it blue. And if it's below the line, I've made it red. So you can see A, B, C, D, E, F, G, H, I, J, this double bond, they're both above the line. They're both blue. K, L, M, again, both above the line, both blue, and back and forth. Everybody got that? Everybody see the pattern there? When you hydrogenate, you get rid of some of your double bonds, and some of your double bonds you convert from the cis double bond, I and J are on the same side, to a trans double bond. You see now I've shifted I and J to opposite sides. All you have to see for the pattern here is here we have all blue and then all red below, and now I've got blue and then the blue comes down here. That rearrangement of the structure of the carbon bond, that's a trans bond, and this is a trans fat. Trans fats exist in nature in relatively low amounts. Bad news, there's a little bit of trans fats in butter. But when we hydrogenated oils to make margarines, to make semi-solids, we created lots of trans fats. And those trans fats were shown to be a huge risk factor for cardiovascular disease. Such a risk factor that the United States in 2018 banned them from their food supplies. So you will find no trans fats. Well, let me take that back. There's a little grace period for things to actually get off the shelf. They could put them on the shelf, but they could sit for a long time because there were lots of preservatives in them. So you might still find some trans fats on a grocery store in a really rural place somewhere out, but anyway. But nowadays, there are no trans fats. And the challenge was that all of these foods were heavy in trans fats. Yeah, cake, cookie, popcorn, microwave popcorn, yeah, lots of trans fats. So manufacturers had to figure out how to create semi-solid lipids, or had to take healthy oils and figure out how to make them semi-solid to replace all the trans fats that they now suddenly had to get rid of. So we've now shifted from a process of hydrogenation to a process called interesterification. We are not going to go into interesterification. You will run out of here screaming, boys. No, we will not do that. But in a nutshell, because I'm doing a lot of nutshell science here, you take a liquid, an oil, and you blend it with a solid lipid, a fat, That liquid generally has a lot of double bonds. The solid has very few double bonds. You blend it and you actually add an enzyme that rearranges the order of the 3 fats on each of those triglyceride chains and incorporates some of the saturated fats into the liquid and some of the unsaturated fats into the solid. And at the end of the day, you get something that is semi-solid but produces no trans fats. So somebody asked me at the break, we were talking about margarine, and that the margarine of today is different from the margarine of 3 or 4 years ago because it had to be manufactured in a completely different way without hydrogenation. So there are people you can go to, there are websites where people feel very strongly about this, and they'll say, my favorite brand of margarine now tastes different. They have ruined it. They've changed the recipe. Yes, because your favorite brand of margarine was actually causing cardiovascular disease. So they had to change it. And you know, it's interesting. We went through this in the 80s where suddenly all fast food restaurants had to quit using animal fat to fry their food. And they all went to vegetable fats that had been hydrogenated. And we argued that it was healthier. Was not healthier at the end of the day because we added in all these trans fats in all of the food that we ate. So let's talk about fats and your health. No guilt. This is a guilt-free zone. Remember, I just fed you all butter. We need fat from our food. It is a requirement in our diet to have fat. It's an energy source. There are more calories in a gram of fat than in a gram of, say, carbohydrates. So it is a way that our bodies store energy for when it's needed. Fat helps us absorb vitamins and minerals. It's a critical component of the membranes around our cells, which we'll talk about in just a minute. It helps protect the sheaths around our nerves that help insulate our nerves. And it plays a key role in things like muscle movement and blood clotting. You need some fat in your diet. And we have done ourselves a disservice in this country because we said fat is the enemy. And all our foods got rid of fat, but it no longer tasted very good. So what did we put in it instead to replace it? Sugar. And lots of refined carbohydrates. And so we said, I'm eating no fat. This is low-fat ice cream, but it is loaded with sugar, but it's low-fat. We thought we would see a change in our incidence of obesity. Yeah, it was all changed, but it just kept on going because people mentally said, there's no fat in this, it's low fat, I can eat more of it. Or yeah, I can eat a cookie because I have low fat XYZ. So what does the data show us? And the science is really challenging to get a good handle on. But in general, saturated fats are not something you want to make the primary component of your diet. Some saturated fat is okay, but you do not need to be getting most of your fats from saturated fats. It increases, diets high in saturated fats lead to the development of health disease and can increase your cholesterol levels and raise especially your LDL, the bad cholesterol. Let's talk about diets that are high in monounsaturated fats. So these are things like olive oil. So this is the Mediterranean diet. It appears to have a neutral impact on your cholesterol levels. You can get this in olive oil, peanut, canola, avocados, most nuts, safflower oil that is high oleic, which means it has a lot of oleic acid in it. Not all safflower oils are high oleic. This is traditionally that Mediterranean diet. So there's a lot of data that people that have a Mediterranean diet have a healthy lifestyle. Some of that probably is because most of their fats are coming from monounsaturated fat in olive oil, but they also eat a lot of nuts, they eat a lot of fish, they eat a lot of whole grains, they don't have a lot of processed foods, so that kind of all goes together. It's not just if all my fat comes from olive oil, I'm good to go. There are lots of other pieces around that. And then let's talk about polyunsaturated, so diets that are high in polyunsaturated. So this looks like it actually reduces some of those cholesterol levels. So saturated raises, monounsaturated seems to be neutral, polyunsaturated seems to reduce. And you see a lot this term, omega-3 fatty acids. An omega-3 fatty acid is a fatty acid where if you look at the end of that carbon chain and count back 3 carbons, that's where the first double bond is. So an omega-3 fatty acid is simply telling you the placement of a double bond. An omega-6 fatty acid is actually 6 carbons back from the end of the chain. There's something about the oils that have omega-3 and omega-6 that have some sort of beneficial quality. Exactly what that is, it's still being worked out. But these polyunsaturated fats, especially your omega-3s and your omega-6, and you can see on the screen where you're likely to find foods that are high in omega-3 and foods that are high in omega-6. This has a lot of information on it. So I'm just gonna put it here and let you peruse it at your leisure. But essentially, here are a whole set of oils, our margarines, fats. And what you can see is the dark blue is the percentage of fat that is saturated. Now let me come down here. Coconut oil. 90% of coconut oil is saturated fat. Coconut oil is really popular right now. I just want you to recognize if you have replaced all of your fats with coconut oil, you are having more saturated fat than if you are just eating sticks of butter. I'm not telling you shouldn't be doing that. I just want people to realize that there's a high amount of saturated fat in coconut oil, which is something that people often think about as a healthy oil. Butter, here's where we are. Butter, 62% saturated fat. Canola oil, it's about 5% saturated fat. Monounsaturated fats are in orange. Here's our olive oil. Lots. The majority of olive oil is monounsaturated fat. That's the oleic acid that we've been talking about. That's the primary component of olive oil. And then in yellow and in blue are the omega-3s in yellow and the omega-6 polyunsaturated in blues. And you can see, for example, soybean oil has a whole lot of omega-6. Salmon, minus the skin, has a whole lot of omega-3. And then we've got other combinations of fats that are in green. So lots of different profiles in all of the different fats that you can get in the grocery store. What about vegetable oil? So vegetable oil is often canola or soybean or some blend of canola and soybean and safflower, so it really is a mix. So that's where it becomes really important to actually look at the label to see what blend is actually in there. And then here's our Country Crock and our Smart Balance that we talked about, and you can see they have different profiles because they are composed of different combinations of oils, of soybean and palm kernel, or canola and olive and palm. So you're going to end up with different fat profiles there as well. A lot of content in this slide to take a look at.
Just to back up a little bit, I've seen commercials with Country Crock that are advertising plant butter.
Ooh, yes.
Is plant butter margarine?
So there are lots of, so Country Crock is one example, but there are lots of margarine producers that are today advertising plant butter. And so those are taking oils that are primarily found in plants. That might be soybean, that might be safflower, that might be olive, and they are using interesterification, that process, to make margarine from it. But it has no dairy, it has, maybe it has avocado oil in it, for example. So it is simply a different blend of oils that they have used interesterification to turn into a semi-solid so that it is spreadable. Yeah, that's a great point. And you've got some things like, I can't believe it's not butter. The reason you can't believe it's not butter is because they've added cream, or they've added whey, they've added milk solids to it. It still has a better profile than butter, but they've added back some milk products so it has that flavor of butter. Read your ingredient list. Well, attempt to read your ingredient list. It is challenging to work your way through that. Okay, in our last 10 minutes, there are two key concepts that I want to touch on because they're important for where we're going to go next. I told you that one of the commonalities of lipids is that they don't mix with water, or they mix very poorly with water. We need to jump a little bit deeper into science, so we're going to just dip the toe into science a little bit more here. There are molecules, I told you that we're talking about covalent bonds, the sharing of molecules. There are molecules that are not good sharers. They do not play well together. They are the child that takes all the toys and won't give them to anyone else except when the teacher is looking at them. So what happens, they hold on to the electrons that they are sharing with someone else a higher proportion of the time. It's not a 50-50 sharing. And electrons have a negative charge. So if I'm holding on to more electrons, I actually have a more negative charge most of the time. And whatever I'm sharing with, so let's say that I'm sharing with Hugh, I'm not giving him electrons very much. So Hugh has a partial positive charge because he's not getting the electrons that we agreed to. I'm hanging on to him a whole lot, and I've got a negative charge. Polar molecules have poles, like magnetic poles, a partial negative if I'm hanging on to the electrons, and a partial positive if I'm not getting the electrons. So that means that these molecules can potentially, because they've got partial charges, they can attract other molecules. Because if I've got a partial negative, Hugh and I are hanging out together, and I've got a partial negative on my end, and Hugh's got a partial positive on his end, and Julie comes along, and Julie's got a partial positive, and I've got a partial negative, we're going to also make some connections. So these polar molecules have poles, like magnetic poles. They have different charges, and they can have attractions. If you would like to just let that roll right on out of the room, I'm okay with that. I just want you to recognize that some molecules do this. Water is notoriously polar. It has this partial negative on the oxygen and these partial positives on the two hydrogens. And I've just put negative and positive, but they're partial charges. They're not always negative and not always positive. It depends on how the sharing works. And what that means is if I've got a lot of water in solution, I'm going to be able to form these very temporary bonds between the partial positive on the hydrogen of one water molecule and the partial negative on the oxygen of another. So these are very weak, transient bonds. It's almost like I'm just kind of holding hands and letting go and holding hands and letting go, but I'm holding hands enough that I'm creating some bonds. So if you take a container of water, a glass of water, and you pour water up to the top and you keep on pouring, you actually get a surface, you get extra water over the top of the glass, but it forms a dome. Part of that, not all of that, but part of that is because these molecules are still holding on and hanging on. Not entirely, but so there's a significant strength there in that water. The challenge is that oils are not polar. They don't have that same issue. They share relatively evenly, and they don't end up with these partial positives and partial negatives. So if I pour a whole bunch of oil into a container of water, what happens is that there is nothing in these oil molecules to do any kind of sharing with the water molecules. And so the water molecules are like, I don't like you. I'm going back to my other water molecule because we can share some. And in this process, there's a separation of oil and of water. The same is true if I took that pat of butter and wiped it on my hands and then went to the sink and turned on the cold water and put my hands underneath. The water just beads up. There is no interaction. There is no, unlike if I had salt or sugar on my hands, the water actually surrounds those salt and sugar molecules and dissolves it off. Doesn't happen with fats. So there's the two things I want you to take away from this section. Water and oil don't mix. There's a polarity and a non-polarity issue. And then the other thing is this concept of hydrogen bonds, this temporary hand-holding between molecules, because this is not the last time you're going to see hydrogen bonds. Hydrogen bonds are critical to the way our proteins shape so that they actually do their job. Your red blood cells carry oxygen because of hydrogen bonds. They're critical to the way your DNA holds together. Our DNA is a double helix entirely because of hydrogen bonds. If we didn't have these kind of transient linkages, we would be in big trouble. And I just want to lay that out for us. Last piece. Let's talk about lipids in our cells. We've talked about lipids in our food. We've talked about lipids in fats and oils. In your cell, lipids, fats, play an incredibly critical role. And that's due to this molecule right here. So this is a phospholipid. Let me show it to you in chemical form right here. So here is a saturated fatty acid. Here's an unsaturated fatty acid. There's our double bond kink. And instead of having another fatty acid and making it a triglyceride, I actually am bound to this molecule, which is phosphate and 4 oxygens, and then this molecule up here, which is choline, that includes carbons and hydrogens and a nitrogen. So this is familiar. We've seen this. This is different, and here is what it looks like in a space-filling model. Here's your saturated fatty acid, here's your unsaturated, and then here's your phosphate and your choline. This is probably one of the most critical molecules in your cell. And this structure, I've already told you that your fats don't like water. They repel water. Another phrase for that is they are hydrophobic, fear of water. They do not like water. This piece, though, up here up top, is quite happy with water. It'll happily interact. It's hydrophilic. It is water-loving. It has lots of ways for water to interact. It's got some polarity around it. So what you end up with is you get what's called a phospholipid, phospho because it's got a phosphate. It's got a water-seeking head and a water-repelling tail, 2 water-repelling tails. And in your cell, these molecules line up in a double layer. You can see here are the heads and here are the tails, and then here are the tails and here are the heads. This forms the membrane around every single one of your cells. Every cell in your body, every cell in any animal, plant, bacteria is composed of 2 layers of phospholipids. So the lipid in the inside and the phosphates on the outside. And that makes sense because inside your cell is a mostly water-based environment. And outside your cell, there's a whole lot of stuff happening in a water-based environment. So this lipid layer, this bilayer, helps separate what's outside the cell from what's inside the cell. And the water-fearing, the water-repelling molecules help keep the water from dissolving into our cells. They keep that water out. So every cell, and then the parts of your cell, your mitochondria, the energy powerhouse, surrounded by a double layer of phospholipids. Your nucleus that stores your DNA, surrounded by a double layer of phospholipids. So these phospholipids are critical for us to be able to carry on individual cellular function and not just be a bag of enzymes and proteins without any kind of structure. So that's the third. We talked about oils, we talked about fats, and we talked about phospholipids. Key components. So here's our take-home messages. Congratulations, you have made it through Lipid 101. Well done. I know we covered a lot of chemistry. Lipids, fats and oils, are long chains of carbons and hydrogens. And they're joined together, 3 of them joined together in a triglyceride. You've got different lengths. Some are 4 carbons, some are 18 carbons. Some of them have no double bonds, they're saturated. Some of them have 1 or 2 or 3 double bonds. The length of the fatty acid and the placement of double bonds gives important characteristics to how those fats function. If they're liquid at room temperature, if they're solid at room temperature, if they're saturated, if they're mono or polyunsaturated. They have different flavor profiles, they have different health benefits, different health challenges. The process that we've gone through technologically to try to create non-butter substitutes was fraught with challenges like trans fats, which we didn't really realize were a health issue until they were. So we've now got other technologies. Science marches on. And fats are a required part of the human diet. So the no-fat approach is not doing you any favors. Now, neither is the I'm going to eat a whole lot of saturated fat. That's not doing you any favors either. So don't walk out of here and say, Dr. Lamb said I can eat all the fat I want because fat is an important part of my diet. Yeah, that's not quite what I said. Now, next week, so we're going to move on from lipids, from fats, and we're going to talk about proteins. Oh my gosh, we're going to talk about proteins. And let me just give you a hint of where we are going next week that potentially will be enough to draw you back in spite of the chemistry. To see if this is the reality, you will have to come back. Next week, we're going to talk about proteins. So I'll be up here if you've got questions, because I realized we didn't have a lot of time for questions. Drive safe tonight. Have a good night. Thank you for being here. Good night, everybody.